Hello, this is Gus from 3DeepLearner.com, and this is the second installment in our SIGGRAPH 2018 series, where I discuss the papers you have voted as the most interesting in this year's event. In this video, I'm going to be talking about mode-adaptive neural networks for quadruped motion control, which is a paper that, well, as you guessed it, talks about motion control. Motion control is what we use to control characters in real time and, do smooth transitions from runs to walks in all different directions and so on. Historically, that has been done with state machines, and you have some data that has, it's highly structured. You have several different clips, they're tagged, their inputs, their, the beginning and ends, they like kind of match, and maybe you have some algorithms to optimize transitions and so on. So what the authors are trying to do is to simplify that process using neural networks and learning from unstructured data. That had actually been previously done, or a part of it had been done in a previous paper called Phased Functional Neural Networks, which actually shares some authors with this paper. And that previous paper talked about bipeds, and the current paper solves the problem for quadrupeds, which is a harder problem. Okay, in the previous video, I talked about how neural networks are good function approximators. If you haven't watched that video, I encourage you to do it. If you haven't read our article on how neural networks work, I encourage you to read that also. Okay, the links will be in the description for this video. Well, this problem we're talking about of motion control, it could be described in a function like this. We have an input trajectory, and we want to get the character's pose. Okay, so let's try to draw that. Let's say I have the trajectory is, what the user inputs. So let's say the user wants the character to move forward and then, walking. And at some point, he decides that the character needs to run to the right. Okay. And we want to know from this function which should be the character's pose at this instant right here. So I hope you can see that this right here is not enough information to determine this right here. Why? Just because we have the speed and the direction, we can't really tell, like for example, if his foot is touching the ground, if his left foot is forward or if his right foot is forward, if he's in a contact position or in a dowel position or in a passage position. There could be many correct answers for the same input. And when a neural network has many correct answers for the same problem, what it does, it averages out all the results. Okay, so this is what a neural network would produce if these were the inputs and outputs. Okay, so a better approach to do this would be to give it more inputs. So for example, we give it the trajectory and the prior pose. So if we say trajectory was so, and the prior pose was a contact, it knows that the next pose should be a down. Okay, so it makes the problem simpler for the network. This is what a network would output if those were the inputs. Note that this is a lot better. It's actually very usable in comparison to what we have seen before. But the authors of both of these papers we're talking about, they have noticed that the averaging effects in the feet, you can see that both in the biped and in the quadruped. And they proposed different neural networks that reduce this averaging effect even further. So this is kind of the idea behind the PFNN paper, and you would have like several different networks, and each one of these networks specialize in a different part of the movement. Let me just get a different color pen right here. And let's say you have the beginning of the movement, and this is going to be learned by the first neural network, and then you have this part of the movement is going to be learned by the second one, and this part right here by the third, and so on. Okay, you have a parameter, which is called the phase, which is basically just looking at the foot contacts to determine this beginning and end, and then you blend the neural networks these specialists, these expert neural networks, depending on this phase parameter. Okay, so this is from the PFNN paper, and although this is a very interesting idea, it doesn't work for quadrupeds because you can't really create a parameter called phase for quadrupeds that matches walks, paces, trots, gallops, and so on, because they all have different foot patterns that don't really match. So the authors used a different approach called mixture of experts, and what this does is that the network learns by itself in which points of the movement and in which movements it should specialize in. So you have different networks that specialize in different parts of the movements, and the networks learn how to do that by itself. Okay, let's talk about how this was actually done. So at the beginning you have a simple neural network that doesn't specialize at all. It just could be applied to all samples and have that averaging effect that we talked about. This is what it looks like. It has one input layer, one output layer, as you would expect. It has two hidden layers, and they're 512 neurons each. So it looks a lot like, it's the same topology of the network we saw last week, which is an indication of how many problems you can solve with, just one simple neural network structure. This is a very different problem, and you pretty much have the same topology. This is also a regression network. Okay, we're not trying to classify the winner. We're trying to get the values of activation and construct an output from them. And that's basically it. So these are the inputs and outputs. You have as inputs the character's trajectory. Okay, this trajectory is composed of 12 points. The 7th point right here is the current time. And you have 5 points into the future, going 1 second into the future, and 6 points going 1 second into the past. Each of these points has the position relative to the current position, and the direction and the velocity. The direction and velocity, they kind of, if you think about it, you think they would have the same direction, but the character can drift or sidewalk and so on, so they can be different. And there's also a parameter here, the desired speed, and also a parameter called the style. So the style would be something like if the character is idle, or if he's walking, or if he's jumping. So, depending on the input that the user is gonna give you, pressing this button or that, you want to trigger a different style. And you have the trajectory plus the position, rotation, and velocity of all of the character's joints at t-1. So this is important because we want to give it the prior pose, and we want to extract from it the current pose. So in the current, in the output, you have the trajectory starting at t+1. You don't care about the past, so none of this. And you care about the trajectory going 1 second into the future. You have 6 points right here, so if I recall correctly. And starting at t+1, and the joints for the character, which we get the position, the rotation, and the velocity as well, they are in the current time. Okay, so this is what the inputs and outputs for the network look like. As you can see, this is not the data you would get from your mocap system. So these trajectories and these velocities, they need to be calculated. So there's a pre-processing involved. Okay, pre-processing. And these styles, they really have to be annotated by humans. So there's annotations, okay, human annotations. So this is probably, this involves a lot of work in coding, and this involves human labor, okay? Well, then how does how do the authors make this network or make specialist networks, expert networks out of this basic topology? Well, if you remember from our previous articles and videos, what the neural network actually learns is the weights. And these networks, they are all fully connected as the one we have seen previously. So these connections between one layer and the other, they hold weights. And these weights, they are what the network actually learns. This is the memory of the network. And what the authors do is they create variables where they store different sets of weights. So you would have the red weights, and you would have the green weights, and you would have the yellow weights, and so on. So it's actually as if you had different networks altogether, although they share the same topology. And each one of these experts, they receive a coefficient, okay? And they are blended across, using this coefficient. So let's say at any given instant, I want to use 70% of this expert and 20% of this expert and then 10% of these other two. Okay, so we're gonna load this multiplied by this factor and then add to this one and add to this one and add to this one, and we would construct a new set, final set of weights that we're going to use to predict the result. Okay, but how do we actually do this? How do we learn these coefficients right here? Okay, so for that purpose, we have something called the gating network. The gating network, its topology looks pretty much the same as the one we have in the motion prediction network, but the output layer is actually a softmax. We've talked about softmax before. I encourage you to watch the previous video where I explain it a little bit more in depth. But what it does, it looks through the activations in these neurons and it enhances the winner. So let's say, for example, that the green here was the winner. And it's going to enhance that. It's not going to trash the other values, but it's going to diminish them. And it's going to fit the sum of all these values up to 1. Okay, so the sum of all activations would be equal to 1. So this is pretty much what we want from our coefficient. We want it to add up to 100%. So let's say, for the sake of this example, this would be 0.7, 0.2, 0.1, and so on. So this is what the weights actually look after activation. But how does the network learns that? It receives as input a subset of the original input that from the motion prediction network. It's actually just 19 parameters, which are basically the 1 point in the trajectory and plus some information on the position and velocity of the feet. And based on that, it's going to pick a winner. But how is it going to pick a winner? We don't have data for that. We're not telling it how to do so. But remember, neural networks, they have randomly initiated weights. So whenever you initiate this network, they're not zero. So this is naturally going to make some parts of the motion trigger one expert and other parts of the motion trigger other experts, and so on and so forth. They might be the wrong experts at the beginning, but this is gonna be enhanced through the learning process. Okay, so about the learning process, the loss function is the MSE, the mean squared error, which we talked about, which just takes the distance, the square distance between the final activation and what our data shows we want. It's gonna take the distance, and then it's gonna change the weights from this layer to this layer so that these activations more closely match what we want, and then the backpropagation algorithm, which is how the network actually learns, is going to do the same for this layer and this layer, this layer to this layer, from this layer to that layer, from this layer to this layer, and so on and so forth. So this layer is trained at once all together. You could break parts of it and train them separately. This approach exists, but this is not what the authors did. So it actually learns how to make one expert better for that task and which expert should be used in each task. Okay, so this is how it learns. I haven't talked much about backpropagation in my blog, so backprop. I'm gonna put a video in a link in the description of this video to another video that covers this, and I really encourage you to look at that. Okay, so this is how the network learns. I'm gonna show you the demo provided by the authors. I think that gives you more intuition. Okay, this is the demo provided by the authors. I'll have the link in the description for this video, and I'm gonna encourage you to download it and click here on these visualizations they have, the one for the expert activation. So here you can see this is the output of the gating network. There are coefficients for each expert, and each one has a color, so you can easily detect which one is which. And you can clearly see we have a winner right here, and we have the values for the other ones, but they're down there. And if we change the character style, for example, let's say if I make it sit down, it's going to change that balance of experts. If you're going to make it lie down, it's going to change that balance of experts once again. You know, you change the winner and the balance between the winner and the losers. But if we are in a cyclic action like this, you'll see that for every part of the action, there's a different expert. So like for a simple walk, there is a blend between like 4 experts right here. If I run, there's kind of 2 that are more prominent, and then a third one that is right down there. And if I jump like this, there's 1 expert that is really expert in the movement where the character has all the feet off the ground. Okay, and I think this gives you an intuition of what's going on. So these are the coefficients, and these are the actual final weights based on the blending of the weights given that those coefficients. So the weights of the network are always changing so that to better represent that instant of the movement, which is really interesting. Okay, well, back to our presentation. So how this has been implemented by the authors. There are several different components of this. I told you there is some pre-processing has to be done in the data that is done by the authors in Unity, and then they bring that data using CSV files to TensorFlow. They train the model in TensorFlow and bring the weights of the network in a binary format back to Unity. And in Unity, they actually implement the network. They re-implement the network once again using C# and a C++ library called Eigen, and load those binary weights to the model, and thus can give you the prediction. So all of this is available in the GitHub, the author's GitHubs, and they have all the code for the training, the pre-processing, the runtime character control. They also give us access to the data, both the pre-processed data and the original data. So it's really rich in information. And what I have tried to do to lower the barrier of entry to all this code for you is I have created a supporting article in my blog, 3DeepLearner, where I talk about how to use all of this with the data provided by the authors, and also using your own data. I use the CMU dataset as an example, but you could really use any data you'd like. It is very modular. There are some GUIs for the pre-processing and the runtime character control. So I really encourage you to look at that. Okay, let's go to the ending of our presentation here. So discussion. This paper is really interesting for many aspects. The first is the data set. I mean, this data set, it's like half an hour, I guess, of quadruped motion in all different, sitting, standing, walking, running, trotting, and so on. This is not easy to come around. You can actually get a lot of human data, but quadruped data is not easy to get. So this is a great contribution. This paper, it expands what had been done in the PFNN. The PFNN has a lot of human annotation of floor context, the face itself, and so on. And here, the only human labor you need is to detect the style, if it's sitting, walking, idle, and so on. And that's it. And it actually produces less feet drifting. So it's really, really interesting in that case. It has less annotations, and it still has less drifting, which is great. And finally, the one limitation cited by the authors is that they do not yet cover changes in the terrain. So the changes you see in the demo, they are done with an IK. They are not tackled by the neural network, but there is really no reason why that can't be done. Maybe it just hasn't been done yet. So I hope you have liked this. Next week, in 2 weeks, I'm going to be talking about deep mimic, and really nice paper also. And if you enjoyed this, if this has been helpful to you, I encourage you to share our links in your social media or with your colleagues. Thank you very much, and see you in 2 weeks.